Hello everyone, welcome back. This is Calculus 3. So in this video, we are going to talk about 3.1 vector valued functions and space curves. So this is a new chapter. So in this section, we're going to extend the concepts from earlier chapters and also examine new ideas concerning curves in three-dimensional space. We're going to see a couple definitions and theorem to support the new idea in terms of vector valued functions. So I will take a look at what the vector value function in this section. Let's take a look at it. So the definition, vector valued function. So as you know, we talk about the vector form in chapter 1 and 2. So you can write in two different ways. So let's say I have a vector. So we can write it either 2, 3, 1 if we are talking about this in three-dimensional space, or we can also rewrite it 2i plus 3j and k. And ijk, this is a standard form such as a 1, 0, 0, 0, 1, 0, 0, 0, 1. Like it's like a basic unit. So you can write either this or that way. What we are going to do, vector value function is a little bit different from the regular vector we talked about before. So in the vector value function, your component, these are the component of the vector. The component has another function format. I know, sounds interesting. So for example, in vector value function, vector R, let's say, you can rewrite it f of t, g of t, or h of t. So what I'm saying is the component is not just single number. The component is another form of a function, okay? So for example, as you see that in this vector, it is not just vector, it is specifically vector value function because your three components, are changing depending on the t variable. So the first component is f of t equal to radical t. And then the second component is also function t squared. And then the third component is changing depending on the t. So as a t is changing, right? Each component is changing. So this is exactly the relationship between input and output. And each component, as you see that, has another function form. So depending on the t, the f, g, h function is going to be changing. So that's what the vector value function. So you can think about it. It's not single number. Each component, so these are the component, has a function form. Okay. So therefore, each component, gonna have domain and range because they are function. Okay, so if we are talking about vector value function in two-dimensional space, we have a f and g. In three-dimensional, we have a three-component f, g, h. So that the component are real value function, okay, in terms of the t. So that you can write it either f comma g or f comma g comma h. So this is the vector value function. One more time. This is not just vector. Your component has a function form. So depending on the parameter t, the function is going to be changing because it's an input and output relationship according to the definition of the function. Okay, so let's take a look at the example. So the more we practice, the more we have, and you can build up the better confidence. So I have a space here. So let me just keep using the same example. So let's say one more time, I have a vector vector valued function. So this is the given, which is each component has a function form. So radical t, t second, ln t minus 1, correct? So this is a vector value function. If t is 1, the vector is going to be 1, 1, and it's going to be, ln 0 is going to be 1. And then if your t is 2, your vector is going to be changing. So this is the vector value function because each component has a function. So let me write it one more time. So in this vector valued function, there are 3 functions as a component of the given vector, correct? Specifically, the f of t, the first component is the f function, radical t. The second component is a g function, t second, and h, the last one, ln, t minus 1. We are looking for the domain where it consists of all value of t for which our vector, the value vector function, is defined. Okay, I want to define this value vector function, and I want to find out the domain that defines this value vector function. So what I'm saying is, I'm going to show you that work. So let me minimize a little bit. To determine the domain for this vector valued function, we must investigate each component's domain. So let's take a look at the domain of each component. So what happened? We can see f of t equal to radical t. So to find out the domain, this is only valid when t is greater than or equal to 0. Inside of the radical, we cannot have the negative number. So when t is greater than 0, this function will be valid, correct? So that's the domain for the f function. Second, the g function as a t second power is valid when t is all real number. So we are looking for the domain for the quadratic function. So if you remember, quadratic for domain can be any number, negative infinity to positive infinity. The last one, ln t minus 1, again, this is valid when t minus 1 is greater than 0. It means t is greater than 1. So we have the domain such that for the f function domain is greater than or equal to 0, all the positive numbers. Second, g function domain is a negative and positive all real number. The last one, t is greater than, the domain is going to be 1 to positive infinity. So these are the domain. Am I correct? And let me just minimize a little bit one more time. So now you're going to find out the domain of, so now we're going to find out the domain of the vector value function, okay, which is the interval where they're intersected. So first one, we have a 0 all the way up, positive. And then the second one is all negative, positive. And then third, we have a 1, all the positive. So this is the common area. So this is going to be the domain for the vector value function. So this is each component's domain. And then the commonality, the common area, that's the vector, the domain of the vector value function. So it is going to be 1 to infinity, where all 3 component functions are valid. that's a period. So that's how we can define the vector value functions, domain and concept, more specifically. Okay, so that's what the definition of a vector value function. You're gonna take a look at the component, and the component is a function form, so that to find out the domain of vector value function or it's a characteristic, you need to take a look at, you need to investigate the components, domain, and it's a function form. Okay, so that's the concept I want to really introduce in 3.1. So likewise, we're gonna keep looking at more examples so that I can give you a better understanding. Let's take a look at the next example. Okay, so we got the concept, what the vector value function. So let's go down slowly. So one more time, I'm gonna write it, vector value function, right? A vector value function, okay, is where each component is a function form. So let's look at the question. We have this vector, and they say it's a vector function. Why? This all vector is a vector value function because why? When you look at each component, definitely because each component is a function form such that your f function first, such that your f function, the first component is a t function, linear, and then your second function is a quadratic function, and then the last component, t second plus 1. So this is definitely defined as a vector value function because each component is a function form, FGH. Literally, this is not single number. You can find out the domain. So we just verify that. Now, what the real question? They want you to evaluate when t equal to 0 and 1. So exactly, since this is a vector valued function, the outcomes are changing depending on the input. Does it make sense? Function means you have input and output. So we have input 0 of this vector value function. So what happened? This is what? F0. The second one is a Z0. And then the next one is H0. So we can evaluate it. When 0, it's going to be 0, G function, -1 and 1. So this is the component when input is at 0, especially when t equal to 0. Does it make sense? And then this outcome is going to be changing if you have a different input, 1. So F1, G1, H1. So if you calculate it, 1, if I plugging in 1, this is a 0, this is a 2. So as you see that, the outcomes are changing depending on the input. So that's you can keep observing the structure of the vector value function. Does it make sense? So I'm gonna keep practicing so that you can feel, oh, this is a vector value function, okay? So let's take a look at the next example. I'm gonna change the color. Here we go. Okay, now they are asking, find the domain. Okay, this is the vector value function. Why? The R vector given is a vector valued function because I check each component of this function is a function form, correct? More specifically, the first function component is a radical t minus 2. Second component is also function ln 8 minus t in terms of t. And the last one is 1 over t minus 4. So I see that this is the function form in each component. Now they want you to find out the domain. We have to find out the common domain. So let's find out the domain for the first one. The t minus 2 should be greater than or equal to 0. It cannot be negative number inside of the radical. So t is greater than 2. So the domain, what? Including 2 all the way up. And open parenthesis, it's an infinity. And then second one, 8 minus t cannot be negative number, should be positive number. So if you solve it, t is less than 8. So domain will be all the negative and stop 799999999. That's a domain for the second function. And then the last function, we are looking for the domain. So the denominator cannot be 0. That's the definition of the fraction. So t is not going to be 4. So you have all real number except 4. So this is the domain for the last function. So you have these 3, right? Domain of each component. I'm looking for the entire domain, commonality. So the first one from 2 all the way up. The second one, stop 8 and go down. And all real number, but the common area is, and then except 4. 4 is not going to be there. So your area of the domain is going to be here. This is the domain, including 2, stop 4, and do not include. So open parenthesis and do not include 4. So this is the domain. The domain of our vector value form is 2, 4, union 4, 8, where all 3 component function are valid. So that's your answer. And just a little bit of note for your understanding. You remember, if you do not include A and B, we are making the open parenthesis, correct? If you do include A and B, we are using the bracket. So you see what I'm doing? We are including 2, so bracket, and then we do not include 4 and 8. That's open parenthesis. So this is the domain of this entire vector value form, R vector. Got you? So far, I talked about the definition of the vector value form and it's a characteristic, by looking at the component of that vector. So now we are going to talk about more and more characteristic in terms of the vector value function. So let's take a look at it. So since, right, the vector value function, when you look at the component, it's a function. What that means is you can find out the limit as well. So for example, we have a vector value function, ft, gt, and ht. Let's say this all vector, I don't know, maybe it looks like something like this. Okay, let's say this is all vector. Let's say as t is getting close to a certain number, where this vector is actually heading to. I want to find out this one. So this is exactly the limit concept. So as you see that this is a vector R, okay? As t is approaching to a certain number, where this R vector actually is heading toward, that's a limit. So therefore, to find out that specific number where this R vector is reaching out to, as t is approaching to a certain number, you just put the limit of each component, put the as t is approaching to the certain number a. So we can say, I'm going to highlight it. We can find the limit of the vector function, the vector value function, because you can take the limit of each component of function. So therefore, if you want to find out R vector, right? And then as a t is approaching a certain number, I want to know where they're actually heading to. Simply, you're going to take the same limit of each a, f, and g, and t. So this is the limit of a vector value function. Okay. And one tip we learned in calculus 1 and 2, if you remember, when you try to calculate the limit value, if you find out the infinity over infinity or 0 over 0 or undefined case, do you remember? Consider the L'Hopital's rule, which means you're going to take the derivative of each top and bottom so that you can take the limit of that complicated indeterminate form of the function. So let's take a look at that question. Here we go. So here, we have a vector value function. This is actually, I'm going to copy, go up, 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 up. I'm going to copy this same sentence, copy this all vector. As you see that, yeah, this is also vector value function because each component has a function form, correct? And in this time, they want you to know as t is getting close to 0, where this vector is heading to. So we are taking the limit. They want you to find out the limit value as t approaches to 0 in terms of this vector value function. So what happened? We're going to use this definition, correct? So we are looking for limit t is close to 0 with this r vector value function. So that means you're going to take the limit t is 0 with the f function. So in this time, f is 1 plus t second, comma, limit 0, t times e negative 1, comma, limit sine t over t. So we are going to find out the limit of each component. Does it make sense? So that's the definition. So how do you remember how to take the limit? So we are going to use a direct substitution, right? So here, you're going to use direct substitution. So 1 plus 0 square 1. So limit, the first component as t approaches 0, it's going to be 1. And second one, same, direct substitution, 0 times e to the, actually my typo, this one should be t. So let me change this question. So this is not 1. So this one also should be t. So let me change. So this is t. So if you're plugging in 0, what you're going to get? It's a 0. So 0 times 1, it's anyway 0. So second component, we got 0 as a t getting close to 0. So the last one, if you're plugging in 0, it's a sine 0 over 0. Dun, 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 dun. If you remember sine 0, it's going to be 0 over 0. This is undefined. So we don't have an answer for, the limit. No, you have to use now L'Hopital rule. So which means you are going to take the derivative. So limit t getting close to 0, sine t over t, you are going to take the derivative. So what is it? It is going to be d over dt sine t over d over dt t. So sine t, if you take the derivative, it is going to be cosine t, t is going to be 1. So basically we are taking the limit of cosine t. So what happened now, you can use a direct substitution. Cosine 0, it is going to be 1. So this last function, when you take the limit as t approaches to 0, you will get 0. So we got the answer, final answer. So here we got 1, 0, 1. So this is where this vector value function, right? As t is getting close to 0, here this vector is going to be 1, 0, 1 in 3-dimensional space. So that's how you can consider taking a limit to find out the outcome, as t is getting close to a certain number. Okay, so just remember, since components, the components of this function is a function form, so you can take the limit. Okay, so let's practice a couple more. Let me go down slowly. Just 2 more examples in terms of the limit. So in this question, I want you guys to find out the limit of this vector value function. So these are all vector value function. because the components are function form. And actually, I want to find out where they're going to heading to as a t approach to 3. Okay, so the first question, we have a 2 f and g. So our vector, this is in 2-dimensional space. So the vector, the components are going to be 2 second minus 3t plus 4, comma 4t plus 3. So it means you have f and g, and I'm looking for limit t approach to 3. So this means you're going to take the limit of each component, t squared minus 3t plus 4, comma limit 4t plus 3. So always the first methodology, it is going to be the direct substitution. I'm just trying to smaller. So if you're plugging in 3, this is going to be 3 squared, 9 plus 4. This is a 12 plus 3. So basically you will get 4 and 15. So this is the outcome of this vector value function when t is getting close to 3. Does it make sense? So that's your answer. One more example, bottom. So this is also vector value function because the component is a function 2t minus 4 over t plus 1, comma t over t second plus 1, 4t minus 3. I want to find out the limit. So we are looking for limit as a t approach to 3, rt. It's the same as what? Limit 2t minus 4 over t plus 1, limit t approach 3, t over t second plus 1, limit t approach 3. So we are going to take the limit of each component, correct? So we are going to evaluate it. You can use the direct substitution. What are you going to get? So if you're plugging in, so let me just minimize it. Actually, maybe I don't need a space. So let me get rid of it. So if you're plugging in t equal to 3, so this one will be 2 times 3 minus 4 over 4, 3 over 9 plus 1, 10, and then 3, 12 minus 3. So if I simplify, this is going to be 1 over 2, 3 over 10, and 9. Yep, that's where you're going to get as a t approach to 3 in terms of this vector value function. So you can get the answer very simply. If you want to write another form, it's the same as 4i plus 15j. This is the same as 1 over 2i, 3 over 10j. By using the standard vector, you can also write this way too. And ijk, you know what that means. So that's how you are evaluating the limit of a vector value function. Are you guys okay with that? Okay, so I'm gonna just couple more example, just couple more practice. Let's take a look at the bottom example. Here we go. So in this question, same thing, we are going to evaluate the limit of vector value function, but not only find out the outcome, but also they want you to take the limit and find out the domain both. Okay, so let's do both work here. So we know this is the value vector function. So you want to take the limit. That means you're going to take the limit t approach to 1, 3t, and limit t approach to 1, t squared. So by using the direct substitution, 3 times 1 and 1 square. So basically 3, 1, this is the, your limit as a t approach to 1. So you can rewrite it 3 plus j. And I want to find out the domain. So what is a domain? Domain means you're going to find out the domain of each. So f of t, 3t, domain would be all real number, correct? So this is a linear. G function is a quadratic, same thing, all real number. So what is a domain of this? Let's say this is RT, the value vector function. So therefore, the domain of vector R is also negative infinity to positive infinity. So that's where the, our vector will be valid. Okay, that's it. Let's take a look at a couple more, just one more. I'm gonna change that color. So let's evaluate the limit first. So the limit t approach to 2, t second limit, t minus 2, t second minus 4, limit approach to 2, t second plus, and then we have a t minus 2. So you're gonna plugging in 2. Let's just see what happened. This is going to be 4. And then what happened? This is a 0 over 0. Dun, 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 dun. We have to use L'Hopital's rule. So you are going to take the derivative top and bottom. That's the L'Hopital's rule. So you are going to take the d over dt, t minus 2 over d over dt, t second minus 4. So what are you going to get? This is going to be 1, right? The bottom is going to be 2t. So now you are going to take the limit, t approach to 2, 1 over 2t. So 1 over 4, that's the second component's, limit. And then we're going to do the second one. What are you going to get? This is also going to be 0 over 0. Yeah, so 4 plus 4 minus 6 over 2 minus 2. 2 over 0, this is undefined form. So we have to take the derivative according to the L'Hopital's rule, right? L'Hopital's rule. So you're going to take the derivative one more time, d over dt, t second t minus 6 over d over dt, t minus 2. So 2t plus 1 over 1. So now you're going to take the limit of that. So let me actually minimize it a little bit. So we are going to take the limit, t approach to 2, 2t plus 1. Now you're going to get 5. So what happened? This is going to be 4, 1 over 4, 5. This is where, you're going to get as a t approach to 2. This is the limit value. And let's find out the domain, right? The domain, think about it. It's not complicated. The domain, this is the function quadratic. So domain is going to be negative infinity to positive infinity. And then according to the second, this is a fraction. So the denominator cannot be 0. So the second component, t second minus 4 cannot be 0. That means t squared cannot be 4. That means t cannot be plus minus 2. So you can have all real number except plus minus 2. Same thing, the last one, the denominator, t minus 2 cannot be 0. So you can have all real number except t equal to 2. So what is your answer? If you think about it, we have all domain, but except minus 2, plus 2, they are the problem, right? They are the problem. So you cannot include them, plus minus 2, because these are my exception. So that you have all number except this. So you can say the domain will be all real numbers except plus minus 2. This is the domain of this vector value function where it is valid. Does it make sense? So think about it. We practice both how to find out the domain of the vector value function and the limit value. So that's the, pretty much the work we can focus on in 3.1. Got you. All right, so I'm not gonna do this one. It's the same question. You can keep practicing it. Try this yourself, okay? All right, so now I'm gonna talk about one more thing. So if you guys remember in calculus 1, you remember the continuity of the limit. You are not able to find out the limit all the time. There's actually require where the given function is a continuous. So we have to prove that the vector is a continuous. That means there's no hole, there's no break. So to find out the continuity of the vector value function, there should no hole, no break. And the definition of the continuity, you have to satisfy this 3 things. Okay, so let's take a look at it. So this is just two-dimensional space. We have a 2 component and this is a 3, depending on the situation. So if you remember the vector here, let's say we have a vector R, let's say T. I want to prove that this is a continuity, which means there's no break, no hole. So how to prove that? When you have certain number like, T here equal to A, you have a, plugging in A into that function. So R of A, that's going to be when T equal to A. And also you're going to take the limit as a T approach to A. And then if those are two information equal to, right, your answer, your given vector is going to be valid as a continuous function. Okay, so that's a definition. I will show you the example. So the example is not that crazy. So let's take a look at it. I'm going to go down. So it's going to be 2 or 3. So here we go. Okay, this is a vector value function. I want to prove that this vector valued function is continuous. So we need to check those two and then check they're equal to each other. So first of all, the R vector is e to the t sine t and ln t, correct? And then let's find out, when t equal to, so I don't know what the, vector look like, but I want to know. So let's say we have R vector. I want to know, well, when t equal to pi over 4, what is the outcome? So let's evaluate pi over 4. So e to the pi over 4 sine pi over 4 ln pi over 4. You can use a decimal. It's going to be the decimal. That's okay. So this is a 2.19, comma, 1 over radical 2. This is going to be negative 0.24. So this is the outcome when you have a t is a pi over 4. Let's find out the limit as well. So limit t pi over 4 RT. So you are going to take the limit of each component, correct? So e to the t, limit t approach to pi over 4, sine t, limit t approach to pi over 4 ln t. So you're going to plugging in to evaluate the limit. So let me minimize it. So this is going to be, if you take a look at it, e direct substitution, e to the pi over 4. This is a sine pi over 4. This is ln pi over 4. Actually, you're going to get the same number, 2.19, 1 over radical 2, negative 0.24. So what we just did, we just proved that these two are equal. So therefore, this value vector function is continuous at t equal to pi over 4. We just verified that. Sometimes it's not continuous depending on the t. So you have to, read the question carefully. Usually the t equal to a, the a value is going to be given. So you can check when this vector value function is continuous at that moment. Okay, so that's how you're checking the continuity of the vector value function. Just check it out, whether the given function and limit is equal to each other. That's it. All right. So we are almost done the basic concept of vector value function. Let me just take a look at one more, the idea in terms of the vector value function. So let me go down slowly. So you might be wondering, Professor Ben, what is the vector value function look like? I want to see that. So graphing vector value function, this is not really, the textbook, they don't talk about this, but I want to show you more visually. So let's take a look at a little bit of a recall. So now we know that vector value, the general vector, we know that vector consists of direction and magnitude, and it is considered to be in standard position if the initial point is located at the origin. So we know the vector looks like this. This is the just, regular vector, including direction and magnitude. So when you are graphing the vector value function, it is going to be very similar, but it has a component, right? Vector has a component, and vector value function say that each component has a function form, right? So what I'm saying is, let's say you have a vector ft, gt, and ht. This function coming from the x-axis, the second function coming from the y-axis, the last function is coming from the z-axis. So it's really, really difficult to imagine this abstract, concept, but you can think about it. Okay, this is, let's say, I'm gonna say, this point is ft0, gt0, and ht0. So this is where the three components are meeting at t equal to t0. And think about this one. I know it's a little bit abstract, but you can think about this is where f function from the x-axis, specifically when t equal to t1. I'm just giving you the random number. And then this is a g t1, h t1, and then this is going to be rt1, isn't it? So this is rt0. Same thing, you have another one from the three component function. So when you collect all this rt0, rt1, rt2, they are going to be create kind of like a line, like a curved line. So this is all the collection of the vector value function as a t is changing. Am I correct? One more time. This is the line for which this is the collection of all the, the r vector as a t value is changing, but this is not simply just one point. Each point from the component function. Okay, so like a double idea. So we call this one is actually, we're gonna call this is going to be same thing. Actually, later I'm gonna show you. It's the same as parametric equation because it is in terms of t. Again, plane curve, well, we are just dealing with the two vector, and then the space curve when you're dealing with more the more components of the vector value function. So there are two names. Plane curve, you have only two component. Space curve, you can consider three-dimensional, so you have a more like f function in the component g and other component. But basically, whenever you are trying to graph of this vector value function, they're going to be equivalent to parametric equation. So this is a little bit abstract, and the textbook, they don't cover this, but I just want to give you more information. Vector value function, it's a simple. You can calculate it, you can evaluate it, you can find out like all the domain, and you can do it more algebraically. But I want to really give you the idea what they mean visually. So each component, right, is based on the component function. So when t equal to 0, you collect that information. When t equal to 1, you collect that information. In three-dimensional space, it's more complicated, right? And then when you are actually connect all these vector points, they're going to be like create a curving line, and then that is going to be parametric equation. Does it make sense to you? So think about it, and I will show you just a couple examples. Not that difficult, so let's take a look at it. So exactly, I want to find out the space curve, which means if you graph the vector value, this is what I'm going to graph it. So think about it. You have t equal to 0, so you're going to evaluate the three thing, and you're going to t equal to 1, you're going to evaluate the next one. So when you graph all this, component, you will find out like kind of the line. But let's do it mathematically. So we know that RT is a sine t, cosine t, and t. And then we know that this is from the x-axis, This is from the y-axis. So this is a general form before I'm going to have a specific input for t. And this is from the z-axis. Mathematically, I can set it up because this is from the x-axis. So I can set it up x equal to sine t, y equal to cosine t, t equal to, z equal to t. Z equal to t. And now, according to the trigonometric function, what happened is, let me just square everything. So it's going to be x second, sine second t, y second, cosine second t. Why am I doing it? Because if you are adding sine second t plus cosine second t is going to be 0. So that means from this equation, x second plus y second, you can say sine second t plus cosine second t. That means y second plus x second plus y second is 1. So we found out in somehow Cartesian equation from this vector value form. And then if you actually graph it in 3-dimensional space, this is going to be the cylinder, isn't it? So if we have x, y, z, so I don't have a z value, so z is open, you will find out this is cylinder. This is the 3-dimensional space circle equation. The cross section is a circle. And then this is your equation, x second plus y second equal to 1. The radius is 1. This is a cylinder. And then actually, if you point out all this numbers, so when t equal to 0, so sine 0, cosine 0, 0, when t equal to 1, sine 1, cosine 1, and 1, they're going to create a curve inside of this cylinder, which means in somehow you will find out this. So they're going to be, this is the parametric equation of the cylinder. So this is vector value function. So this is the graph of a vector value function. So this spring also create a cylinder, and we checked by converting it to the Cartesian, we found out the cylinder shape. So they are going to be, this is the parametric equation of this cylinder, and then we call this is helix. This is the helix, that's the name of this space curve. But again, I just want to give you guys idea. You don't need to really prove it, but think about it. Although textbook, they don't talk about it, but I just want to show you, like what the mean vector value function in visualize. Usually we are using computer, but I just want you guys think about, by using your hand, okay? So that's what that is. If you actually graph it this one, you will find out that spring, and that spring actually create this, space, looks like a cylinder shape. And then we check that exactly that is a cylinder equation. Okay, so one more time. I told you this is space curve. This is space curve. This is the graph of vector valued function. And actually we call another name parametric equation. So that's the helix we just found out. But so when you create this space curve, sometimes they're creating the cylinder, depending on the shape, or sometimes they're creating other like a cubic shape. It's very, very variety. We don't need to know everything right now. Just remember, space curve, it's a graph of the vector value function, and then you will find out the parametric equation. So let me just do one last example. So let me just do the same concept we just talked about it. So this is the same question, so you can think about it. So we have vector value function. So you can set it up. This is x, y, z, right? We just did it. And then x squared, same thing. Cosine second t. Y second is sine second t. So x second plus y second. That is a cosine t plus a sine second t. So this is 1. So we found out this is a cylinder. This is a cylinder where z is open. And then if you really point out all like r0, cosine 0, sine 0, 0, r1, cosine 1, sine, you're gonna collect all the one. but we are not going to do it by hand. It's too much work. But what I'm saying is you're going to collect where's R of 0, R of t. They're going to create like this is spring. Exactly. It is indicating the cylinder shape. So same thing, we just did it, but I'm going to do the bottom one. Okay, you can do the same work. So here we have 3 components. So I'm going to calculate it. So let's say this is X, this is Y, this is Z. So you can say X equal to T times sine T, Y equal to T, Z equal to T times cosine T. And then I feel like I can do something X and Z. So X squared is a T squared sine square T, Z squared T second cosine second T. So I can adding them up. So X second plus Z second, T second sine second T plus T second cosine second T. So I'm gonna make a little bit of space. So what is going on? X second, Z second. I can combining T second, sine second, cosine second T. So this is gonna be 1, correct? So we have T squared. So this is going to be the, what is that? This is going to be the Cartesian equation in terms of, T. And then this is exactly circle. This is also cylinder, kind of. Cylinder, where the radius is T. And then if you graph it, now there's Y is missing. So X, Y, Z. So Y is missing, Y will be the center. So this is the cylinder equation of that. And then what happened? In this equation, right? What do you guys think? Since the T square is getting larger, so it's not really cylinder, but let me just write it one more time. So the radius, I'm gonna write here, as T increases, Y, not Y, X and Z are in X and Z increase. So think about it. As a T, the radius is getting larger and larger. X and Z is getting larger and larger. So this is the work. So as a T is getting larger and larger, the X and Z, it's going to be larger and larger. So this is kind of like the shape you can imagine. It's not exactly cylinder. Okay, so this is the very interesting equation. This is a Korn equation. So you will find out the Korn. Okay, so if you actually draw all the number, 0 times the sine 0, 0 cosine 0. So it's the first one exactly 0, 0, 0. They're coming from 0, 0, 0. And then as a T is getting larger and larger, you will find out this is spring inside, which means this is the graph, the blue one, graph of vector valued function. And what happened? This equation indicating what? The Korn equation, okay? Which is a slightly different. When you have the above question, it was 1. You have a constant, right? So that the radius was exactly 1. It's a fixed. No matter X and Y is getting larger and larger, radius is always 1. Doesn't matter. But here, as a T is getting larger and larger, X and Z is also larger and larger. So this is the Korn shape, which is a differ. And then you can check by graphing the vector value function as you change the T. So you're going to find out the Korn shape. Okay, so that's how you understand. And this is the parametric equation as a Korn equation. And then this is the circle cylinder equation you found out. Okay, so I just wanted to add this information because you might want to see more visually what the vector value function look like. And then this part, the last part, will be really helpful to understand how how to graph the vector value function and how they are related to the Cartesian you know, the function. It could be cylinder, it could be corn, because they're going to create some shape. Okay, so check it out. And then you can actually, we did a lot of information, but we mastered 3.1. Okay, so feel free to email me if you have any question. Keep working and engaging with other people through the discussion board. Now you can finish 3.1 quiz, and I will see you guys in the next video. Thank you, everyone. Bye-bye. Oh, I just want to say something. Read textbook. All right, I will see you guys in the next video. Bye-bye.